Right now, at this exact moment, the ground under your feet is turning through space at thousands of kilometers per hour. The sun is spinning like a giant wheel of fire. Distant galaxies twist slowly in the dark, and even the most mysterious objects ever discovered, black holes, refuse to stay still. Rotation is everywhere. It is silent, it is constant, and it carries a secret that reaches back to the beginning of time itself. Scientists look into the sky and see a pattern that repeats again and again, from tiny particles to massive galaxy clusters. Nothing seems frozen, nothing stays perfectly still. The question that shakes physics is simple yet deep. Why did motion start in the first place, and why did it never stop? Somewhere in the early universe, long before Earth existed, long before stars lit up the darkness, a tiny imbalance began a chain reaction that still controls everything today. Many people learn that planets spin because of gravity, but gravity alone does not explain the first push. The real story begins with clouds of gas, larger than solar systems, moving with slight uneven motions that no one noticed at first. Those small motions grew stronger as matter collapsed, and like a hidden memory locked inside space, rotation became permanent. In this video, the truth behind cosmic spinning will unfold step by step, using real science explained in clear and simple language. You will discover why motion survives for billions of years, how the law of angular momentum acts like an invisible rulebook for the universe, and why even the slowest turning galaxy holds clues about the moment everything began. There is also a lesser-known side to this story that rarely appears in basic textbooks. Some astronomers suspect that spin may not just belong to planets or stars, but could exist on scales so massive that they challenge how people think about the universe itself. While the debate continues, new research hints that rotation might be more fundamental than anyone expected. This journey will connect everyday experiences, like watching a spinning top or a skater turning faster by pulling their arms inward, to events that shaped entire solar systems. The goal is not only to explain what spins, but to uncover why perfect stillness may be impossible in nature. Along the way, surprising facts will appear, such as how a tiny imbalance in a cloud of dust can create a star, why space has almost no friction to slow motion down, and how the rotation of Earth slowly changes over millions of years without most people even noticing. Each part builds toward a bigger realization. Spin is not just movement, it is a record of history written into matter itself. By the end of this video, viewers will understand how the first cosmic motions turned into the days and nights experienced on Earth, why galaxies look like giant spirals instead of shapeless clouds, and how scientists use rotation to measure hidden forces that cannot be seen directly. The story moves from the birth of stars to the edges of modern physics, revealing that the universe behaves more like a vast dance than a silent, empty space. There will also be moments that challenge common assumptions, such as the idea that things eventually slow down and stop. In space, stopping is rare. Once an object begins to rotate, it can keep going for billions of years unless something powerful interferes. That simple rule explains more than most people realize.
10,
from the shape of Saturn's rings to the violent spin of neutron stars
6,
that rotate hundreds of times every second.
3,
This introduction
2,
is only the first
1,
step into a deeper exploration where
booster
physics
ignition,
meets
liftoff,
mystery,
Space Shuttle
where
Discovery,
tiny motions
taking the
create
space station to
enormous
full power for
consequences,
full
and where
science.
every rotation tells a story
This is
older
Mission
than Earth
Houston.
itself. Stay with this journey until the end,
Roger,
because the
roll,
final
Discovery.
sections connect all the pieces
Discovery's
together
roll
and
maneuver is
reveal a
complete. It is
perspective
now in a
that
heads
changes
down
how the
position
sky looks
on track
forever.
for its flight
The
to
spinning
the
of
International
planets,
Space
stars,
Station.
and galaxies is not random chaos. It follows hidden laws that scientists are still trying to fully understand, and the
Discovery
answers
flying
bring us closer to one of the
365 miles
biggest
per hour,
questions in science.
1.5
Why does the
miles in
universe
altitude,
move at
7
all?
miles downrange
Each
from the
minute
Kennedy
ahead
Space Center.
uncovers another layer, building from
Discovery's
basic
engines are
ideas
throttling
to
down as the
mind-bending
orbiter passes
insights
through the area
that
of
show how a
maximum
small
pressure on the
beginning
vehicle.
can shape an endless future. If curiosity about space, time, and the forces that guide existence sparks even a small sense of wonder, then this video will take that curiosity much further. It is designed to break complex ideas into clear thoughts, to reveal lesser-known details that many people never hear, and to turn a simple observation into a powerful understanding of reality. Welcome to our channel, where deep questions meet clear explanations, and the universe becomes a story that anyone can follow. Subscribe now and stay connected, because the journey into the spinning cosmos is only just beginning. Across the vast darkness of space, a quiet pattern repeats itself again and again, yet most people never stop to notice how consistent it truly is. Every planet known to science spins around its own axis, some slowly and some so fast that their shapes stretch slightly at the equator. Earth turns steadily, creating the rhythm of day and night, while Jupiter rotates at an incredible speed that makes one full turn in less than 10 hours. Move farther outward, and the same behavior continues. Distant exoplanets discovered around other stars also rotate, even when they exist in environments completely different from our solar system. This constant turning is not limited to planets alone. Stars themselves rotate, carrying enormous oceans of plasma around their centers. Our sun spins quietly, with its surface taking about 27 days to complete a rotation, while massive stars in distant regions can spin so quickly that they flatten like spinning disks. When astronomers look even deeper into the sky, the pattern grows larger instead of fading away. Entire galaxies twist through space, forming graceful spiral arms that stretch for hundreds of thousands of light years. These structures resemble giant storms frozen in slow motion, turning patiently across cosmic time. From small moons to vast galaxy clusters, rotation appears again and again, as if written into the rules of existence. The idea that this could be coincidence becomes harder to believe with every new observation. Scientists have mapped thousands of galaxies, and a huge number of them show clear signs of spinning motion, moving like cosmic hurricanes that never lose strength. Even black holes, objects known for swallowing light itself, often spin at extreme speeds, dragging space around them as they rotate. The deeper astronomers look, the more obvious the pattern becomes. Movement is not rare in the universe. Stillness is. This repeated rotation forces a deeper question to rise. Why does motion continue for so long without fading away? On Earth, spinning objects usually slow down. A toy top loses energy because of friction with the air and the surface beneath it. A bicycle wheel eventually stops turning when left alone. Yet in space, many objects keep spinning for billions of years. The answer begins with a simple but powerful idea known as angular momentum. In basic terms, angular momentum is the tendency of an object to keep rotating once it has started. It acts like a promise made by motion itself. If nothing interferes, the spin continues. This rule is not just a theory created by scientists. It appears everywhere in nature. A rotating planet carries angular momentum. A spinning star carries even more. When astronomers calculate how galaxies move, angular momentum becomes one of the most important tools they use to understand the structure of the cosmos. The reason this rule works so strongly in space comes from the environment itself. Space is nearly empty. There is almost no air, almost no resistance, and very little friction to slow things down. Without friction, motion does not fade easily. A spinning object can keep going long after anything on Earth would have stopped. That is why a planet that began rotating billions of years ago still turns today. The same idea explains why a neutron star, born from a collapsed star, can spin hundreds of times every second without losing much speed. Once motion begins in the vacuum of space, it becomes incredibly difficult to erase. Understanding angular momentum also reveals why rotation often speeds up instead of slowing down when matter gathers together. When a cloud of gas shrinks under gravity, its particles move closer to the center. Because angular momentum must stay balanced, the rotation becomes faster as the size decreases. The effect resembles a spinning skater pulling their arms inward, causing their turn to speed up dramatically. This principle shapes entire solar systems. During the formation of stars and planets, collapsing clouds of gas do not remain slow and calm. They spin faster as gravity pulls them inward, creating flat disks of material that later form planets. The hidden rule guiding all of this is not mysterious magic, but a natural law that operates quietly in the background. Even though most people never think about angular momentum in daily life, it controls events on scales far larger than imagination. The spinning of Earth, the rotation of the sun, and the graceful motion of galaxies all follow this same invisible guideline. Every rotation seen through a telescope is evidence that once something started moving, the universe allowed it to keep going. To understand where the first spin came from, it is necessary to travel back to a time long before Earth existed, before the sun ignited, and before the familiar shapes of planets filled the sky. In the early stages of cosmic history, vast clouds of gas and dust drifted through space. These clouds were enormous, stretching across distances greater than entire solar systems. At first glance, they might seem calm and quiet, but they were never perfectly still. Tiny motions existed everywhere inside them. Particles moved slightly faster in one direction than another. Small differences in density created gentle currents that pushed matter around. These uneven movements were subtle, almost impossible to notice on a small scale, yet they carried the seeds of future rotation. When gravity began to pull parts of these clouds inward, the tiny motions did not disappear. Instead, they grew stronger. Regions with slightly more mass attracted more material, causing collapse to begin. As the cloud shrank, angular momentum forced the forming structure to spin faster, turning a loose cloud into a rotating disk. Within these spinning disks, new stars ignited at the center, while leftover material gathered into planets that inherited the motion of their birthplace. This process repeated across the universe countless times. Giant clouds collapsed into spinning systems, each carrying a unique pattern of rotation shaped by the small irregular motions present at the beginning. No cloud started perfectly balanced. Even the smallest difference in movement was enough to create a lasting spin once gravity took control. Over millions of years, dust grains collided and stuck together, forming larger bodies that continued to rotate as they grew. Some planets ended up spinning rapidly, while others rotated more slowly depending on how matter collected around them. The early history of the solar system likely involved countless collisions that changed rotation speeds and directions, yet the basic rule remained unchanged. Motion that existed at the start survived through every stage of development. The planets that circle the sun today carry echoes of those ancient motions, turning quietly as reminders of a time when the solar system was only a swirling disk of gas and dust. As astronomers study distant star-forming regions, they see the same story unfolding again and again. Clouds collapse, disks form, and rotation appears naturally as part of the process. The consistency of this pattern across different environments suggests that spin is not an accident, but a direct result of the way gravity and motion interact. Even chaotic regions filled with exploding stars and powerful radiation still produce rotating systems when enough matter gathers together. Computer simulations that model the birth of stars show swirling motions emerging naturally, even when starting conditions seem almost random. This reinforces the idea that perfect stillness is nearly impossible in a universe filled with movement. Every particle carries some motion, however small, and when gravity pulls particles together, that motion becomes organized into rotation. The hidden rule of angular momentum also explains why galaxies form elegant spiral shapes instead of collapsing into shapeless blobs. As enormous clouds of matter gathered in the early universe, tiny variations in motion created large-scale rotation. Over time, gravity shaped these rotating systems into flattened disks filled with stars. The arms of spiral galaxies trace the paths of stars moving through the rotating structure, creating patterns that appear almost alive. Observations show that galaxies can take hundreds of millions of years to complete a single rotation, yet the motion remains steady because space offers little resistance. The vast emptiness between stars allows galaxies to spin almost endlessly. Even when galaxies collide and merge, the combined system often continues to rotate, preserving angular momentum through dramatic cosmic events. Looking at the universe through this lens reveals that rotation is not just a detail, but a foundation of cosmic structure. From the earliest clouds of gas to the fully formed galaxies seen today, motion continues to shape the evolution of everything. Scientists measure the spin of stars to learn about their age and internal structure. They observe the rotation of galaxies to estimate the presence of dark matter, an invisible substance that influences motion through gravity. Even the behavior of black holes depends on how quickly they spin, affecting the powerful jets of energy that shoot outward from their surroundings. Every new discovery reinforces the idea that the universe is not static, but constantly turning, guided by rules that began operating long before the first planet formed. As gravity pulls matter inward and angular momentum preserves motion, a delicate balance forms between collapse and rotation. Without gravity, clouds would drift apart and never create stars. Without angular momentum, collapsing matter might fall straight inward, without forming disks or structured systems. Together, these forces create the dynamic universe observed today. The early motions inside ancient clouds may have been small and uneven, yet they held enough power to shape entire solar systems and galaxies. Even now, new stars are born from rotating clouds in distant regions of space, continuing a process that has existed for billions of years. The quiet spinning of Earth beneath our feet is connected to those ancient beginnings, a direct result of forces that acted long before life appeared. As gravity pulled giant clouds of gas and dust closer together, a powerful change began to appear in the way they moved. And this change followed a simple rule that can be seen even in everyday life. When a spinning skater stretches their arms outward, the turn looks slow and wide. But the moment the arms move inward, the body spins faster without any extra push. The same idea shaped the birth of stars and planets long before any observer existed to witness it. Inside collapsing clouds, particles drifted closer to the center, reducing the size of the rotating region. Because motion cannot simply vanish, the spin became faster and tighter as the cloud shrank. This process did not need an external engine or hidden force. It happened naturally because of the way angular momentum works. A cloud that once turned slowly across millions of kilometers began to rotate more quickly as gravity squeezed it into a smaller and denser shape. The faster rotation flattened the cloud into a disk, and inside that disk new structures began to grow. At the center, material gathered into a young star glowing with heat and pressure. Around it, rings of gas and dust kept spinning, slowly forming planets that carried the memory of that original motion. Each world inherited a different speed and direction depending on where it formed in the disk. Some ended up spinning rapidly, completing a full turn in only a few hours, while others rotated slowly over many days. The same ice skater effect shaped not only small systems like our solar system, but also massive structures such as galaxies. When enormous regions of matter collapsed under gravity, they too spun faster as their size decreased, forming wide rotating disks filled with billions of stars. The beauty of this rule lies in its simplicity. Nothing magical needed to happen for motion to increase. The shrinking of space between particles alone was enough to transform gentle drifting into powerful rotation. As more observations gathered over time, scientists began to notice that this pattern of increasing spin appeared almost everywhere they looked. The reason nearly everything spins comes from the fact that perfect stillness is almost impossible to achieve. In any cloud of matter, particles move in slightly different ways. Some drift a little faster, some slower, and some change direction after collisions. Even if most of the motion cancels out, a tiny leftover imbalance almost always remains. That small imbalance becomes rotation once gravity begins pulling material inward. Instead of disappearing, the leftover motion grows stronger, shaping the future structure of the system. This is why spin appears on scales both tiny and enormous. Atoms possess a property described as spin, Planets rotate on their axes, stars twist with powerful magnetic forces, and galaxies swirl like vast spirals across the darkness. Each level of structure carries the same hidden principle. Motion survives because nothing removes it completely. Space provides very little resistance, allowing even weak rotations to last for billions of years. Scientists studying distant galaxy clusters find that many of them show signs of slow rotation, suggesting that the pattern extends far beyond individual stars or planets. The persistence of spin reveals a universe that prefers movement over stillness. Even when violent events occur, such as stellar explosions or massive collisions, the combined result often continues to rotate in a new way, rather than coming to rest. This survival of motion creates a chain reaction that spreads through cosmic history. A spinning disk forms planets, spinning planets create magnetic fields, and rotating stars generate energy that shapes their surroundings. Some thinkers have taken this idea even further, asking a question that stretches the limits of current knowledge. If planets spin and galaxies spin, could the entire universe itself be rotating on a scale too large to notice directly? The possibility has inspired debates among scientists for decades. Certain studies examine the distribution of galaxies across the sky, searching for patterns that might hint at a large-scale twist in the structure of space. A few observations suggest subtle alignments in the direction of galaxy rotation, raising the possibility that motion might exist on a cosmic level beyond individual systems. Yet the evidence remains uncertain. Many researchers argue that the observed patterns could come from local effects or random variations rather than a true universal spin. Advanced telescopes continue to gather data, comparing the motion of galaxies in different regions to test whether a global rotation exists. If such a rotation were confirmed, it would change how people think about the origin of the cosmos and the nature of space itself. For now, the idea remains open, balanced between curiosity and caution. The debate itself highlights how little is fully understood about the largest scales of existence. Each new observation adds another piece to the puzzle, but does not yet provide a final answer. The mystery stays alive, inviting deeper exploration into whether motion is simply a property of objects within the universe or a characteristic of the universe as a whole. While scientists explore these possibilities, another thought experiment reveals how essential spin is to everything familiar. Consider a universe where rotation suddenly stopped. Without Earth's rotation, the cycle of day and night would vanish, leaving one side of the planet facing constant sunlight, while the other remained locked in darkness. Winds and oceans would shift in dramatic ways because the balance created by rotation would disappear. Planets that rely on spin to maintain their shape might begin to change form under the pull of gravity. Some worlds could become more spherical, while others might experience structural stress as their internal forces adjusted to a motionless state. On larger scales, the absence of rotation would reshape entire solar systems. The disks that once guided planet formation would not exist, leaving stars surrounded by scattered debris instead of organized orbits. Galaxies might look less like elegant spirals and more like dense clusters without clear structure. The motion that spreads stars across wide disks would fade, allowing gravity to pull matter inward in new ways. Even though gravity would still hold objects together, the universe would appear quieter, less dynamic, and strangely empty of the patterns that make it feel alive. Rotation also influences how energy moves through space. Spinning stars generate magnetic fields that shape the flow of charged particles around them. If those stars stopped rotating, the magnetic environment of entire systems would change. The protective bubble that shields planets from harmful radiation might weaken, altering the conditions for life. The fast rotation of certain neutron stars creates pulses of energy that travel across the cosmos like cosmic lighthouses. Without spin, these signals would vanish, removing one of the most fascinating clues astronomers use to study extreme physics. Even black holes, known for their intense gravity, rely on rotation to create powerful jets that shoot outward for thousands of light years. These jets influence the growth of galaxies, spreading energy into surrounding space. A motionless universe would lose many of these dramatic processes, leaving behind a simpler but far less vibrant cosmic landscape. The deeper scientists explore the effects of rotation, the more they realize how closely motion connects to the structure of reality. The spin of Earth shapes weather patterns, ocean currents, and the distribution of heat across the planet. The rotation of the sun influences solar storms that can affect technology and communication. On galactic scales, rotation helps stabilize star systems, preventing them from collapsing too quickly under gravity. Each example reveals that spin is not just a detail, but a guiding force that shapes how matter behaves. Without it, familiar systems would transform into something entirely different. Yet the possibility of such a change remains purely theoretical, because stopping motion across the universe would require removing angular momentum from every object at once, an event that defies known physics. Looking again at the ice skater effect, the elegance of the process becomes clearer. A collapsing cloud does not need external guidance to increase its spin. The simple act of shrinking brings motion into sharper focus, turning slow drifting into powerful rotation. Over time, these spinning systems interact with one another, merging or colliding in ways that preserve their motion. Even when galaxies crash together, the result often continues to rotate, forming new shapes that carry traces of their past. This continuity connects the earliest stages of cosmic history with the present moment. Every spinning object tells a story that began long before humans existed, a story written in the language of motion and gravity. Scientists continue to search for deeper explanations, building models that simulate how small irregular movements grow into massive rotating structures. These models reveal that rotation is not rare but expected whenever matter gathers under gravity. The persistence of spin also raises philosophical questions about the nature of time and change. Motion creates cycles, and cycles create patterns that allow observers to measure passing moments. The rotation of Earth defines a day. The orbit around the sun defines a year. On larger scales, the rotation of galaxies influences how stars evolve over millions of years. Without these repeating motions, time would feel different, less marked by rhythm, and more like a continuous flow, without clear divisions. The connection between rotation and time suggests that motion shapes not only physical structures, but also the way reality is experienced. Even though these ideas reach beyond simple physics, they grow naturally from the observation that everything spins. As new telescopes peer deeper into space, they reveal young star systems still forming within rotating disks of gas. These observations provide direct evidence that the ice skater effect continues to operate today, not just in the distant past. Clouds collapse, disks form, and new planets begin their slow rotation long before they are fully shaped. Each discovery strengthens the understanding that spin is a natural outcome of the universe's behavior. The mystery of whether the universe itself rotates remains open, adding another layer to the story. Some measurements hint at large-scale patterns that could suggest a subtle twist in the fabric of space, while others find no clear sign of such motion. The search continues, driven by the desire to understand whether rotation is simply a property of objects within the cosmos or a feature of the cosmos itself. If spin defines so much of what exists, then the absence of it becomes almost impossible to picture. A motionless universe would lack the swirling beauty of spiral galaxies, the rhythmic turning of planets, and the energetic bursts produced by rotating stars. Gravity alone would shape matter into dense forms without the graceful structures seen today. The difference between a spinning universe and a still one reveals how essential motion is to complexity. Rotation spreads matter outward, creating space for systems to grow and evolve. Without it, the universe might appear more uniform, less dynamic, and far less diverse. The constant turning of objects across every scale hints at a deeper principle woven into the fabric of existence, a principle that began with tiny uneven movements and continues to shape reality with every passing moment. And when everything finally comes together, one idea stands quietly above the rest. Spin is not random noise, drifting through space. It is not a small detail that appeared later. Rotation is a memory written into the universe itself, a living trace of the first movements that began when everything was young, hot, and expanding. Every turning planet, every rotating star, every swirling galaxy carries a message from that ancient beginning. The day and night on Earth, the storms on distant worlds, the glowing arms of galaxies stretching across the dark, are all part of the same story that started with the earliest motion after the Big Bang. What feels stable and permanent is actually a dance that has never stopped. Even now, while this moment passes, the ground spins, the sun turns, and the universe continues its slow and endless rotation, reminding us that motion is the language of creation. Understanding this changes the way the sky looks, because nothing above is frozen or silent. Everything is moving, everything is connected, and every spin is an echo of the origin of time itself. If this journey through the spinning universe opened your mind or gave you a new way to see reality, then support the channel by subscribing, press like so more curious minds can discover these ideas, and share this video with someone who loves to explore the mysteries of space. The next story is already waiting, and the universe still has many secrets left to reveal.